Okay, hopefully folks heard some message about recording in progress there. Okay, so yeah, as I mentioned, the link to the slides is in the chat now, in our Zoom chat, and then I will just go through the slides real quick with the announcements. Yeah, so now that we have the recording on, today is the July 18th, 2024 Rubin Science Assembly. This is going to be a tutorial, a guest tutorial from Valerio Caruba from Sao Paulo State University. So thank you very much, Valerio, for volunteering and being here today with us to share this work you've done with DP0.3 on RSP. That's really great. We really appreciate it. Yeah, the topic is asteroid taxonomic classification with DP0. So yeah, the first thing on the agenda, which isn't always on the agenda, but today it is how to get a copy of the tutorial notebook. So basically, this isn't in our standard set of DP0 tutorial notebooks, so it's not in the usual place on RSP. So what we recommend to do is to go to your home directory and then run this git clone command, which basically pulls in the entire delegate contributions DP0.3 git repo if you don't have that already. And then you can use the left-hand file browser to go into this new delegate contributions DP03 directory that would have been made by running this git clone command. And then you can navigate to the asteroid taxonomy subdirectory of this git repo, and then specifically open this taxonomy_carry.ipnd file, which is what we're going to go through today. So is anybody having any issues with doing this? I guess let me know and we can try to go through it together if you want, sharing my screen. But assuming that you got the link that I posted in the Zoom chat here, I think it should be straightforward to copy and paste this stuff. So yeah, please let me or anyone else here know one way or another, whether speaking up or in the chat, if you're having any issues accessing this.
Mine worked.
Okay, thank you.
Thank you.
Okay, and now we're just going to go through our usual announcements that we have regarding news, deadlines, and events related to Rubin and the LSST. So as you've hopefully heard by now, next week there's going to be the 2024 Rubin Community Workshop, which is July 22 to 26, Monday to Friday at Slack in California. There's this link here for the website for the meeting, which has all kinds of stuff like the agenda and so forth. There now is a venue for virtual posters. You can follow that link. I believe it will go to a forum post by Melissa. Did want to note that virtual registration is free, but mandatory to access the Zoom links and workshop Slack space. So you would have needed to register to access those things. And then there are childcare grants from the LSSTDA for attendees. I don't know what the status of the deadline for that is, though. The only other conference announcement we have here is LSST at Europe 6, which is September 16 to 20 in Spain. So yeah, this is just, I think, a standard announcement. The first part, at least, so dp0.lsst.io is your place to go for all DP0 resources and all these science assemblies. And then one specific note for this week is that after this week, we will take a break, and then we'll come back in fall 2024 with our next set of Rubin Science Assembly weekly presentations. Then lastly, we do this during each Rubin Science Assembly, but we just wanted to put out a reminder to maximize awareness about the Users Committee. And that's just a place where you can interact with to, for example, send feedback about your experiences as a member of the Rubin community, using things like the Rubin Science Platform and so forth. So with that, I think I will stop sharing my screen and then turn it over to Valerio so that we can check out this asteroid taxonomy tutorial. So I believe that I just stopped the share.
Thank you very much. I will. Can you please confirm to me if you see my screen?
Yep, I see you in the RSP and I see specifically your notebook. So it looks all great. Thank you.
Thank you very much. So thank you all for being here. I'm very happy to share this first attempt of creating a Jupyter notebook on asteroid taxonomic classifications. And I understand that some people may not be familiar with what is a taxonomic classification of asteroids. So just a few words. Asteroids don't reflect lights from the sun, and the way the light interact with the material on the surface means that the light we receive is different. You can have absorption band at some wavelength in the infrared. For instance, 1 micron, 2 micron is associated with basaltic material. The slope, which is the dependence of the spectra, can be different. So you can have a spectra that is bluer or reddish. So based on a series of features and characteristics of the spectra of the asteroid, you can have a classification of the objects. And there are two main complexes for Asteroid taxonomy, which are the C complex, which are more primitive. The spectrum is flatter. And then you have the S complex, which are reddish. They are more inclined to the spectrum. Special classes like the K, the V, which are associated with the basaltic asteroids. You can see these objects at the very bottom corner of the plot. And you see the two absorption band, 1 micron and 2 microns. So why do we care about this taxonomic classification? Because it's the only way we can have information about the composition of asteroids which are not visited by space probe. And because this may give you key about the formation of the mechanism of the solar systems. For instance, we think that C complex and darker objects were formed closer to this, farther away from the sun, while S complex were formed inside, closer to the sun. So the way they are mixed today is because of mechanisms like planetary migration, scattering by massive objects. So it's not like you have C complex in the inner part and X complex only in the outer part. There is some mixing, but roughly this can give you an idea. Special classes which are very much darker, like D, P, T, etc., they are found farther away in the solar system. For instance, there are a lot of DPT in the Trojan asteroids of Jupiter. So all that is nice and good, but the problem is that in order to do this classification, you need to make a spectrum of the light reflected from an asteroid, and this is available just for a few thousands of objects. For many objects, you can have what is called spectrophotometry, which means you can have information about colors in several bands, like E, G, R, and Z. And based on these colors and color differences, you can actually perform preliminary taxonomy for these asteroids and classify these objects based on these photometric data. There are a lot of surveys that have done that in the past. The most famous one is the Sloan Moving Object Catalog, which are a catalog for about 1,000 objects. More recently, we have the Dark Energy Survey catalog, which has information for over 60,000 objects. But the Vera Rubin survey will provide information on colors and photometric information for millions of asteroids. So it is worth investigating what we can do with the simulated data that we already have. So this is a work that I've been doing with in collaboration with Giulio Camargo and Safwan Aljibai. And the notebook is based on original work developed by Jeff Carlin. So the first step is to run import the customary Python packages, assert the DP0.3 tab service. Also, the data that is available in DP0.3 does not include the same measure axis, so there is a standard routine to transform pericenter information and eccentricity into same measure axis based on the formula key divided 1 minus e. So these are just preliminary setup. Okay, here we are importing data from the minor planet tables and the solar system object tables. We are using a small sample of objects to avoid very large queries, very long queries. So this should hopefully run in a few seconds. And we are including orbital properties and, of course, physical property like the colors in various bands, so that we can actually perform the classification based on photometric model of the Meo and Carré. Okay. So we run these queries. We got 985 results. And at this point, we want to determine the same major axis of each objects and calculate the mean anomaly for the orbits, because this is a useful quantity if you want to actually run a numerical integration of the asteroids. So we do just that. This is just a warning, please ignore it. And so we now have the orbital data, and which is just osculating simulating data. So these are instantaneous elements that will vary with time. And in this figure, we will show what is the location of the object we are interested in for this notebook. We are in between in the central main belt at high inclinations. So high inclinations means essentially larger than since an larger than 0.3. So these are the objects between the 3 to 1 mean motion resonance with Jupiter, which is approximately at 2.5 astronomical units, and then the 5 to 2 mean motion resonance with Jupiter, which is the outer boundary of the central main belt, which is at 2.25 something astronomical units. Day 2-3 mean motion resonance with Jupiter, usually an unofficial boundary. Yes, please. Go away. An official boundary that further divide the central main belt into 2 parts. So you can see that there are 2 regions. There is the inner central main belt and the outer central main belt, and these are concentration of objects. If you're familiar with asteroid families, there are several families that can be found here. One of the most important is the Pallas family. Pallas is the second most largest object. Is also an highly inclined object. You have the Ansa family, which is in the inner central main belt, and several other families like Gallia, Barcelona, etc., that are not clearly visible here because these are osculating elements. They are not constant of the motions, but it gives you an idea. So we are interested in physical properties of the objects. So for this, we need to run first the difference in color. So we run the difference in color G minus I, R minus I, and I minus Z. And everything is very fast. So we have these differences in colors. And this is the locations of the objects in these domains. So they have a bimodal distribution in G minus R and R minus I, and they are kind of concentrated in I minus Z, R minus I diagrams. And the unit of measures for these colors are magnitudes. Please feel free to interrupt me at any time if you have any questions, comments. So far, this is very standard. We haven't done much, and much of it wasn't done before in Jupyter notebooks already published by the Vera Rubin. Here is the part in which I actually try to do some classification. So in order to do that, we need to compute a new quantity, which is the spectral slope. The spectral slope is defined as the color Rg minus Ig divided by the difference in lambda with the wavelength between the R band and I band in the Sloan system. So we compute these differences in fluxes, and then we divide by the difference in wavelength. And this is a plot of the GRE slope in terms of frequency. So this is a normalized histogram. You can see that the vast majority of these objects have GRE slopes around values of 9 and 10. This is usually associated with objects that are more located with the S complex, but you also have objects around 5 percent per 100 nanometers, which are more associated with C complex taxonomies. So this already gives you an idea of what to expect for the asteroid in the regions. There should be a predominance of S complex asteroids in what we have in this sample. And this may be just an artifact of the way we selected the asteroids, which are not all the asteroids in the central main belt, but just a small sample in order to make things faster. Okay, so this is what we have done so far. At this point, we need to understand where each point is located. And for this, we need to apply the DP0.3 2013 classification scheme. So every region in the GRE slope E-Z is associated with specific asteroid taxonomy. So if you are between 5 and 25 in GRE slope, for instance, and you have E-Z lower than -0.25, you are V-type asteroids. If you have GRE slope of less than 5, usually it's associated with S complex, C complex objects. And then you have objects with GRE slope larger than 5, which are associated with the S complex. Special classics like B, X's, K, A, and D usually take precedence over more common classes. So the idea is that if you have an object that is in between classes like the L and could also be associated with S, usually the rarer classification is take predominance. So L objects would be classified as L if they are on the border between S and L. But more or less this gives you an idea of what happens for our objects. And now that we know where they are, we can actually assign to each of these points a taxonomical classification. So this is a very long cell, and there are probably easier way and better ways to do it, but I just did it the brute force way. So I check if every asteroid is inside the region assigned to by the DP0.3 model. And this is a histogram of the distribution of asteroids in the region that we are interested in. So there is a vast majority of S-type asteroids, but then you have a few objects that are C, B, and you actually also have some of these rare V-types and a lot of objects which are N, which are significant, means that they have no classification. They are outside any of the boundaries that we selected for the DP0.3 classifications. So the classification scheme does not work. So just a word of advice. When you do a spectrophotometric classification, is not as precise taxonomical classification by analysis of the asteroid spectra. There are cases of misclassifications, so you need to take these with some caution. But on the other hand, the advantage is also that you have a lot more data. Instead of having data just for a few thousand objects, you have data for hundreds of thousands, or with a Rubin telescope, you will have for millions of asteroids. Okay, so we are almost done. We already have the taxonomic classification for each objects. We can create masks for each of these objects and plot where the C-type, B-type, X-type, etc. are located. And this is very, very fast. And so we see that there is a vast majority of S-type, a few objects that are associated with darker type, a few V-type, A-type, and so on and so forth. So This is what I wanted to show you for this first attempt by our group to produce a Jupyter notebook for DP0.3 data. And this is just a small region of the asteroid belt. We can apply the method for other regions. For instance, we can take the highly inclined inner main belt, outer main belt, or other regions whatsoever of the main belt. We can also compare the taxonomical property of main belt asteroid with objects in other regions of the solar system. Application could be applying this method to the Trojan asteroid of Jupiter, for instance, the Hilda population, which is in a motion of Jupiter between the main belt and the Trojan asteroids, and so on and so forth. And that's pretty much what I wanted to show you today. Are there any questions, comments?
Thanks, Valerio. Maybe could you comment a little bit on, like, for example, how someone would go about doing the first optional exercise you had there of looking at asteroids elsewhere? It looked to me like your query doesn't make any restrictions explicitly on, like semi-major axis, although I would need to look at that again. So it seems like maybe then it's just a matter of, in the downstream plotting code, exactly what cuts you make before you plot. Is that accurate? Or?
Well, you need to go first to the query. Here we are not doing, as you say, we are not doing any restriction in semi-major axis, but we are doing it that after we can compute the semi-major axis here in the cell number 5. So I just wanted to, when I did this Jupyter notebook, I wanted to have a small region which was small enough that I knew well enough that I could go understand what happens in detail. But you can, where it is? Yes. So after you compute the semi-major axis, here you have a mask. We select the central main belt. So you have asteroids that are larger than 2.5, 0.8 astronomical units in A, and smaller than 2.8258, which is the limit for the 522. You can change these values as you like. So I believe that another thing that I did was to, yes, put inclination larger than 30 degrees here. Here, these are the highly inclined asteroids, but you can actually select other values of inclinations. It's very easy to do if once you know where you change the parameters.
Yeah,
Does
can you
that
remind?
answer?
Yeah, that was a great answer, extremely concrete and specific of where he would change it. Can you remind me again why were we looking at relatively inclined asteroids for this notebook, as opposed to, because I think most solar system bodies are relatively not very inclined, right?
Well, it's actually a personal bias. I kind of we studied highly inclined asteroids. We published something like 6 papers on highly inclined asteroids. So I know a few things about the region. And when I wanted to start working on this, I wanted to apply it to a region where I know where the physical property of the objects are. But that's a personal bias. People can be, as I say, you can actually select other regions of the main belt, or you can actually select objects that are not in the main belt at all. It really depends on the parameter that you're using here.
Okay, cool. Yeah, thanks. I just was curious about that. I have another question that's, I think, mostly perhaps more related to the second optional exercise, which is, I noticed in your query there's a cut on having at least 70 detections for the SSO. So to me, it would be kind of interesting to understand or to think about, like, does that, if you wanted to look far away in the solar system, does that severely limit what you could do there? Would you need to bring that number down? Or, does Rubin get more than 70 detections of even very distant TNOs. That would be interesting to me to check out.
No, that's a very good question. I think that people should try to experiment with this number. If you're interested in working with objects that are TNOs or further away in the solar system, probably you should relax a bit this constraint. Also, you can see that here we are selecting objects that are in a range between the solar system object identifier. So you can also relax this constraint. You can actually select all objects, but if you do that, you will get a very long queries. It might take several minutes actually to upload all the data. So there are some things that I did in order to have a faster notebook, but sure, please feel free to play with the parameters as well.
Okay, yeah, thanks. That all makes good sense. Yeah, especially the part about wanting to make the query fast and efficient. Does anybody other than me have questions? I may have one or two more small questions, but I'm happy to not be the only one who asks questions, I guess. Okay, yeah, I had one thing you mentioned was that when you were calculating the slope, right, you were talking about dividing by the difference in wavelength.
Yes.
And you mentioned the SDSS. Are those SDSS wavelengths? Like, do you think are the definitions of these slopes in the literature, are people going to need to make like custom definitions for LSST with the exact LSST filter or bandpass center wavelengths? Yeah, I was just curious.
If you apply in the method of the Mercari, you will need to use the photometry of the Sloan system. And these, you may need to apply some corrections. So I believe that the data that we use here are related to the Sloan data. But
Yeah.
I think
Yeah, maybe. Yeah, I mean, I guess I can imagine in the future people doing two things. You could compute corrections to the LSST photometry to try to put it on the SDSS system, or you could have another version of this DeMeo and Carey paper that sort of customizes it all for LSST to begin with. But I don't know. I don't know either of those authors at all, so I guess I don't know how likely it is that there will be a custom LSST version versus people just computing slight corrections to go from the LSST photometric system to the SDSS photometric system.
we published recently a paper on the use of dark energy survey data for the same purpose. And what we did essentially was something that we discovered a bit late in the work, was that the photometric system of the dark energy survey was a bit different from the Sloan photometric system. So you needed to correct for that. This will be something that needed to be investigated, I think. If we can actually use these parameters for the Vera Rubin system or not. So actually, this is, I think, a very interesting question that could be left open.
Okay, cool. Yeah, I'll try to check out that paper about the DES. I would guess that the biggest differences are in the redder bands where the LSST filters are most different. Sorry, band passes are most different from.
Yes, there are transformations that you can. There is a metric, transformation metrics that you can apply for the flux data. I don't remember the details, but if you go in the DES paper, there is a reference to the transformation metrics. So it's not very difficult to implement, just matrix multiplication. But if you don't do that, you can actually get some slight errors in the classifications, which is not traumatic. It's not tremendous amount of error. I believe that when we did before, the photometric correction for DES was about 10% of misclassification with respect to the photometric correction. But it's something that needs to be done.
Okay, yeah, thanks a lot. It looks like Bob has a question, so maybe we can go to Bob.
Thank you, Valerio. Hey, could you show me where you pulled inclination out of the query?
Sure.
I see it. I see it in the mass cut, but I just didn't see it in the query.
Okay, let me see. I think I'm very not. It's here.
Oh, there it is.
MC
Oh, thank you. I got it. Just missed it.
Okay, I have, yeah, one last question that comes to mind would be, based on your analysis here, did everything look very realistic in the DP0.3 simulations, or were there things that were sort of revealed that you could sort of tell that this was a simulation that didn't exactly have every detailed component in there?
Well, there are two things. There should be more C-type objects, especially in the inner part of the central main belt. The fact that we don't find them could be an artifact of the query that we are doing. So this is something that you can actually also see here. I was expecting to see more objects on the C complex. One thing that we don't have, and this is think that there is going to be a notebook on how to import data tables in DP03. These are osculating elements. This means that they are instantaneous, which means that essentially they change very fast from 1 year to the other. If you want to see structure like asteroid families, clusters, etc., you will need to plot proper elements for these objects. These are constant of the motion. We can run simulations to obtain this data, or you can take them from published tables from Astrodynamics site on other sites that have this information. So if you do that, you should be able to see the asteroid family structure. But here we don't see. We don't see the Pallas family. We don't see the Ansa family. In inclination, you will see that there are alignment of objects like in horizontal line, something like that. This is something that we don't see here because we don't have the proper elements, but it is something that we can do actually. We can actually compute the proper element. We can run simulations on our own and upload a table for these objects. I was working on that a few weeks ago, but never had the time of finishing this method. Or you can actually get tables from published data, but that won't work for simulated DP03 data because these are not real objects; these are simulated data. So the best way would be just to do your simulation, get the proper element, and then upload the table.
Okay, yeah, great, thanks. I think I will stop. Oh no, Douglas has a question. Go for it, Douglas.
Oh yeah, I was wondering way back when Jelko, it was like and Mario Uric and others did a asteroid classification in SDSS using colors, and they defined a pseudo color or a combination of colors using SDSS G minus R, R minus I, and they called it basically the A asterisk color. And they, I don't know if it's all right, I could show I could maybe share a screen briefly. I have the paper
Sure.
up.
I think I know what paper you're talking about. Maybe
it's a
even
2001, I think.
Yeah, it's kind of a classic, or to me at least, as a non-expert.
Yeah, I'm not an expert too. But yeah, so it's yeah, the paper is Color Confirmation of Asteroid Families by Ivizik, Lupton, Uric, and others. And they defined a color called A star, which is which they I guess it's basically a principal axis color of some sort for asteroids. I don't quite remember exactly how they came up with that exactly, but when they plot things, they could plot against I minus Z versus A, and the colors kind of came out. The color of different families kind of came out like this. They color code the let's see, where's the color code for the families? It says somewhere. I don't know. Anyway, these are kind of interesting plots. I was wondering if doing something like that would be worthwhile also for the for Rubin. Maybe not.
Yeah, Douglas, we're getting a request to post a link to the paper.
Oh, okay. Yeah, let me do that. I will add that in the chat.
Yeah, so when you're suggesting doing that same thing for LSST, is the idea just that the colors will be slightly different, I guess, especially at the redder end because the band passes are different, or that you have 10 times more asteroids now and maybe you'll discover some new substructure in the plot or some new small groupings or something?
Possibly. I was not entirely sure what if I had actually an actual question in there other than have you thought about doing a plot where you do like a principal component color versus another color to kind of maybe extract further information? I'm not sure if it's useful. I expect maybe well, Sarah would probably have a better idea about this than I do. Or
Well, one advantage of working with the GRE slope is that then you can apply the Demeyon-Carré reclassification model. So then you can have information about the approach that of the Ivesic paper allow you to get the complex. So you can see the C complex, S complex, V-type asteroids, which are the three main blob that you see in the figure that you show. But in the Carré paper in the GRE slope versus E minus E, you can actually get some additional classes that you cannot see in these color planes. So this is a bit an advantage. And the GRE slope is not very difficult to compute once you have these fluxes defined by difference in colors. So this is why we wanted to do this work in this domain. But you're right. The first work really that inspired the Leon Carré is the Ivesic one. We also, I don't know if I can show you another thing. I don't know if it's relevant, but I don't want to make advertisement to our work, but this is a famous figure from Ivesic. So you can actually do this kind of analysis using the Ivesic approach. It was in 2001, I think, that they did, and you can actually see the S-type, C-type, and V-type objects based on this kind of approaches. But again, if you really want to go into detail, if you want to see the order more less frequent classes, then the only model that I'm aware of is this Demeyon-Carré approach.
Is this paper you're showing, is that published or is that just a draft?
No, actually, it's published. The one on dark energy survey.
Okay, cool. Yeah, I'll have to take a look for it.
Well, if you want it, this is a replication of the same model, but for dark energy data, dark energy survey data. Yes, it's published. It's been published early this year.
Okay. Yeah, awesome. Thanks. Yeah, I think I will stop the recording at this point.